Hello and welcome to this lecture on fundamentals of electric drives. In the last lecture, we were discussing about static rotor resistance control for an induction motor. So, we want to vary the speed by controlling the rotor resistance, and our induction motor is verily a slip ring induction motor. So, that we can insert the resistance in the rotor circuit through slip ring. What we did in the last lecture was that we tried to vary the rotor resistance by using a chopper. Let us briefly review what we did in the last lecture. Now, this is what we were trying here, that we have an induction motor here. So, a slip ring induction motor, and then we had an uncontrolled rectifier in the rotor circuit, and then we rectified this, and then in the rotor circuit we injected a resistance R, and then we connected a switch in this case, and the switch is closed and open to control the resistance. And what we saw here is that the resistance which is seen from this AB terminal is RAB is given as 1 minus delta into R. Now, this delta is the duty cycle of the chopper switch that is connected here. Now, we would like to control this in closed loop. Now, we would like to control the speed. Now, these are the characteristic for various rotor resistance RR1, RR2, RR3 and RR4. As you go on varying the rotor resistance, the curve changes and the speed will also change, because since we have a load torque profile, and if we change the rotor resistance, the speed is decided by the intersection of the two characteristics. Okay. Now, if we want to control this in a closed loop, we have to control this current, that is ID. ID is the current in the DC link. Now, if we can control this current ID, we can control the torque, and if we control the torque, the speed can be controlled. So, let us see a closed loop block diagram of a chopper controlled rotor resistance induction motor drive. So, our total resistance is RR, the rotor resistance, plus the resistance, the external resistance, and we have to vary the duty cycle of the chopper, that is delta. Now, this is achieved in the following fashion. So, we have the slip ring induction motor, we have the rotor, and we have the stator here, and this is fed with the normal 3-phase AC. And in the rotor we connect a diode bridge. So, we have the rotor where we connect a diode bridge like this, and we have this inductor in the DC side, and then we connect resistance here, and we have a transistor chopper which has to be controlled to control this resistance between A and B terminal. So, this is the DC link current ID which we need to control. This is the resistance R. So, what we do here, we have a speed sensor. So, this is the rotor. So, with the rotor we connect a speed sensor. Speed sensor will give us the actual speed, which is omega m, and this omega m is compared with the reference speed. We want to keep a reference speed which is omega m star, and this error is fed to a PI controller. and then the output of the PI controller is limited because we have integrating action. So, the output has to be limited. So, we limit the output of the PI controller. This is a current limiter, and the output of this current limiter is ID star. This ID is a measure of the torque. Now, if you want to increase the torque, ID has to be increased. If you have to decrease the torque, ID has to be reduced. So, by controlling ID, we can control the torque of the motor and hence the speed of the motor. So, the output here is ID prime, ID reference, and this is compared with the actual value of the current. So, we measure the current here and we feed this current here, the actual value of the current. We have a current sensor verily, and this current sensor measures the value of the current and we feed the actual value of the current. Now, this is fed to a PI controller, the second PI controller, PI 2, and then we have the base drive, and this base drive is fed to the base of the transistor. So, what we are trying to do here, we are trying to base drive and control. So, we are trying to control the angle delta. So, this is the closed loop block diagram of chopper controlled rotor resistance based induction motor drive. So, what we have here is that we have a reference speed, we compare that with actual speed and we have the error here, speed error, and then we have a speed controller or a simple proportional integral controller. Then the output of that is the current ID, and ID is also controlled by feeding it from the actual ID. We have a current sensor. So, this ID is fed here, and then the output is again the current error II, this is I speed, the speed error, and we have the current error here, and then that is fed to another PI controller, which will give you a control signal, and the control signal is in fact compared with a triangular wave to generate the gate drive signal. So, we ultimately control the duty cycle of the chopper, so that the current is adjusted ID. So, this shows a closed loop block diagram of a static rotor resistance control of a slip ring induction motor. Now, this is employed for very large power application. As we know that slip ring induction motors are employed for large power application. Now, in large power, the efficiency of the drive has to be good. Now, when we are having chopper based resistance, the energy is wasted in the resistance. So, is there any possibility of recovering this rotor energy? So, if we can recover the energy from the rotor instead of wasting in a resistance, we call that to be a slip power recovery scheme. So, we will be discussing now a slip power recovery based control of slip ring induction motor. So, we will be discussing about the slip power recovery. And this is again used for slip ring induction motor. And also for larger power drive, large power drive. Now, let us see what is the concept of this slip power recovery. Now, let us draw the equivalent circuit of the induction motor, per phase equivalent circuit. So, this is the per phase equivalent circuit of induction motor. We have the stator resistance, the stator leakage reactance, and then we have the rotor circuit, we have the rotor leakage reactance and the rotor resistance. So, what we do here, we insert a voltage source. We insert a voltage source of a specific frequency. This voltage source is VR, and as we know that frequency in the rotor is SF. This is the stator circuit and this one is the rotor circuit. Now, here the induced DMF of the stator is E1, the rotor induced DMF is E2, but we have a slip S. So, this is S into E2. So, E2 is the standstill rotor induced DMF, E2 is the standstill rotor induced DMF. So, S into E2 is the induced DMF of the rotor at any given slip S. The reactance is XR corresponding to the frequency F. Now, the frequency is S into F. So, we have the reactance which is S into XR. The rotor resistance is RR. Now, in this case, let us see the flow of power from stator to the rotor. The stator we are supplying the electrical power, some part is wasted in the stator and some part is crossing from stator to rotor, that is called the air gap power, and from the air gap power a part is converted into mechanical power and the remaining is recovered by the source. So, the power flow will be of this sort. So, we have the input in this case P in and the power which is crossing the air gap is called the air gap power Pg, and the power which is converted to mechanical power, that is Pm, and the power which is absorbed by the source Vf, that is the slip power, that is Pr. Now, let us neglect the rotor copper loss and simplify this analysis. Neglecting rotor copper loss, so we can say that Pm is the output mechanical power, that is equal to the air gap power minus the rotor power which is recovered. So, we have flow in this case, that this power is the input power and then we have the power which is recovered by this the voltage source, that is Pr, and the power which is converted to mechanical power is Pm. So, this is the equation. Now, Pr is the power absorbed by the source Vr, okay, and this is the power which is recovered here. So, this power Pr is being recovered. So, that is why we call this to be a slip power recovery scheme. Now, in the earlier days we used to have something like Schrage motor to recover this, but now we employ static converter to recover this slip power. Let us see configuration using a static converter to recover slip power, and that we call to be a static Kramer drive. So, what we call that to be a static Kramer drive. So, how is this static Kramer drive? And this is used to control the speed for control of rotor speed below the synchronous speed, below the synchronous speed. Let us see what is this static Kramer drive. So, let us draw the input 3-phase supply. We have the 3-phase supply here, and then we have the induction motor. So, this is our slip ring induction motor. So, we are feeding the stator from this 3-phase supply. And we have the rotor is fed to uncontrolled rectifier. So, we have an uncontrolled rectifier bridge, a 3-phase bridge here, which is connected to the rotor through the slip ring. So, this we have. So, we have the rotor phases. So, this is what we have here. So, this is one phase, this is the second phase, and this is the third phase. So, this is what we have here. So, now we have a switch here which we can connect. Similarly, for phase B we have a switch which can be connected, and for phase C we have a switch which we can connect, and it is normally connected to the rotor resistance for starting purpose. So, we have another set of switches here. So, this is a switch, gang switch. This switch is called S1, and we have the switch here is called S2. So, this is the induction motor, and we have the stator to rotor turns ratio is n:1. And then we have the DC link. The DC link is connected to a large inductor, and then we have the SCR bridge, we have a 3-phase SCR bridge here, which is connected to the DC link. The output of this SCR bridge is connected to a transformer. We have maybe a star is to star transformer that is connected to the SCR bridge. So, this is the SCR bridge, and SCR bridge is connected to the input side, the transformer, and the transformer is connected to the same AC line, 3-phase line. So, this is the transformer, and transformer has a turns ratio of m:1. This is the primary. So, this side to this side is m:1 transformer. The inductor in the DC link is LD, and the current flowing through this DC link is ID. The output of the bridge is VD1, and output of this thyristor converter is VD2. So, VD1 is in this direction, VD2 is in this direction. Now, when we start this induction motor, when the induction motor is normally running without any speed control, let us say normally it is running. So, we close switch S1 and turn off switch S2. So, what we do here, we close switch S1. So, this is closed. So, this switch is closed and this switch is open. So, as a result, in the rotor, this is our rotor circuit, and we have the stator. In this case, the stator is fed from the 3-phase supply this is our 3 phase AC line. So, this is the 3 phase AC line AC grid. So, the stator is fed from the 3 phase AC and the rotor is connected to 3 resistors through the slip ring. The motor normally rotates, and when we want to recover the slip power and to do the speed control, we open this switch S1, this switch is open and switch S2 is closed. So, these 3 switches are closed. So, when these 3 switches are closed, we have the connection here. So, the converter, the rectifier is connected to the rotor of the induction motor. This is open and S2 is closed. So, the rectifier is connected to the rotor of the induction motor. Rectifier output is VD1. So, what is this VD1? VD1 is the output of a 3 phase rectifier, which is same as 3 Vm by pi, and if we write the expression for VD1, that will be the following. So, VD1 is equal to, if the per phase voltage V is the per phase source voltage. So, we can say that V is the per phase source voltage RMS. So, if V is the per phase source voltage RMS, the peak voltage is root 2, that is the phase voltage, the line voltage is into root 3, and we have to multiply with 3 Vm by pi, 3 Vm by pi, and since the rotor is running at a speed omega s, the slip here is equal to s. So, the output of this is that into s, we ignore the drops here, and the turns ratio here is n is to 1. So, divided by n. So, the voltage which will appear at VD1 is the following: 3 into root 3 into root 2 V s by pi into n. Now, that is equal to 3 into root 6 V into s by pi by n. So, that is VD1. Now, what is VD2? VD2 is here, and VD2 is coming through a transformer. That transformer is m is to 1 transformer. So, we will write down the expression for VD2. So, VD2 is equal to 3 into root 3 into root 2, again the phase voltage here is also V. So, V is the per phase voltage, RMS voltage. So, that is V here. So, 3 Vm by pi, and the transformer has a turns ratio of m is to 1. So, in the secondary side, this will be appearing as this by m. So, this is the expression for VD2. So, we have the expression for VD1 and VD2, but the output in this case has to be controlled. So, this is a controlled rectifier. So, what we have here is a controlled, it is a converter. So, since we have a converter and this is a rectifier, since we have a converter here, we have to multiply with cos alpha. Alpha is the triggering angle of the converter, triggering angle or the firing angle of the converter. So, VD1 is 3 root 6 V s by pi n, and VD2 is 3 into root 6 V by pi m into cos alpha. Now, we can apply Kirchhoff's voltage equation in this loop. So, in this loop, if we apply KVL, we get the following equation. So, we can say that VD1 plus VD2 is going to be equal to 0 if the inductor drop is neglected. If inductor is an ideal one. So, if the inductor is an ideal one, there is no drop here. So, we can say that V d 1 plus V d 2 is equal to 0. So, we get the following equation. So, we have 3 into root 6 V by pi 3 V m by pi into S plus 3 into root 6 V by pi, this is by N, that is the turns ratio of the induction motor, by M the turns ratio of the transformer into cos alpha, that is equal to 0. Or we can say that S equal to minus N by M into cos alpha. So, S is the slip of the induction motor is given by N by M into cos alpha. Hence, by varying the triggering angle alpha, we can vary the slip of the induction motor. Now, if we want to design the transformer of turns ratio M, so we can say that what should be the turns ratio M here? M and what is S max here? So, S max is nothing but N by M into cos alpha max. So, the maximum value of slip is equal to N by M into cos alpha max. What is the range of alpha? So, this converter is actually operating in the inverting mode. So, converter operates in inverting mode. So, we have the converter which is operating in the inverting mode. So, it means alpha is greater than pi by 2, alpha is greater than 90 degree. So, in this case the range of alpha here is greater than 90 and alpha should be having a maximum value, that maximum is approximately 165 degree. Why it is 165? Because it is operating in the inverting mode. So, we have to have successful turn off of the converter thyristors. So, we can't go directly close to 180 degree, it has to be sufficiently smaller than 180. So, it is approximately 165 or so. So, alpha max is 165. So, in this case alpha max is 165, alpha max, the maximum value of alpha is 165 and it is operating from 90 to 165 and the converter is operating in the inverting mode. It means it is feeding power back to the source. So, the power flow here is, if we see the flow of the power, this is the rotor power which is coming here P r, and this power is fed back to the supply, to the transformer, and hence through the transformer we are able to feed back this power, and hence we call it to be the slip power recovery scheme. And here we have the value of alpha, alpha maximum value is 165 per degree. So, we can have the alpha maximum here. So, what should be the turns ratio of the transformer? If we want to design the transformer turns ratio, that is equal to minus n cos alpha max divided by S max, and this is the turns ratio of the transformer. So, if we want to design a transformer and to find out what is the turns ratio of the transformer for a given value of S max, the slip, and given value of alpha max, we can use this formula to arrive at the turns ratio of the transformer. So, we conclude here by observing that we can vary the speed of the induction motor by controlling alpha. So, this is our equation which shows that the slip of the induction motor can be controlled by controlling the triggering angle alpha of the converter. So, as we go on varying the triggering angle alpha, the slip can be controlled, and slip has to be less than between 0 to 1, and hence it operates in the sub synchronous speed or speed below the synchronous speed. So, we stop here for today's lecture. We will continue with the slip power recovery scheme in the next lecture.